All right, one more example in this section where we talk about the shape of different curves, specifically how the shape is affected by the derivative and the second derivative of a function. In the previous video, we did a lot of drawing. The idea was to sketch an approximate graph of this function by considering when the graph was increasing and decreasing and when the graph was concave up and concave down. What I want to do in this next example is kind of similar, but not exactly the same. This time, I don't want to look at the function algebraically at all. I just want to look at the graph. So suppose we take a look at this original graph and pretend we don't know the equation at all. If we just know the function, maybe we can call this thing f of x. My question is, could you come up with an approximate sketch of the graph of the derivative? It's hard to do. It's really hard to do. But I think if we focus on some specific points, we'll be able to do it. So maybe we'll sketch f prime of x in blue. If you had to sketch f prime of x, where would you start? Well, maybe a good place to start is thinking about when does f prime of x equal 0? Remember, f prime of x tells you the slope of the tangent line to the curve at a given point. And if the slope of the tangent line to the curve equals 0, that means that the tangent line is horizontal. So where would we have horizontal tangent lines? Well, at all of these critical values here, right? At this mountaintop and at this valley bottom and this mountaintop and so on. In a previous video, we labeled all of these different critical values. And since we know all of these critical values correspond with when f prime of x equals 0, we know that if we're going to sketch the graph of f prime of x, the height of the graph should be 0 at each of these different critical values. Now all we have to do is look at the behavior in between these critical values. So to the left of this critical value, so I'm thinking about this part of the graph right here, should the height of my graph in blue be a positive number or a negative number? Well, maybe you can answer that question by thinking about what it means for f prime of x to be positive. If f prime of x is positive, as we saw a couple videos ago, that means my function is increasing. And when f prime of x is negative, that means my function is decreasing. So if I look at my graph over here, this graph is definitely increasing until I get to this critical value. That means my first derivative is positive until I get to this critical value, which means the graph has to be positive for all the values pictured to the left of this critical value. How positive should it be? Well, if you want to be really careful, you could be like, it's barely positive over here because the slope of the tangent line is barely greater than 0. But as I get further and further to the left, the tangent line gets steeper and steeper and steeper. I don't know, maybe it would look something like this. We don't know enough to really get the idea of the shape of this graph in blue, so as long as you have positive values all throughout here, you're doing just fine. What about from this critical value to this critical value? What about on this interval right here? Well, the hiker's going downhill, right, from this mountaintop to this valley bottom, so my graph is decreasing throughout this interval. The fact that my graph is decreasing means my first derivative is less than 0, so the height of this graph in blue should be less than 0. How much less than 0? Well, I don't know. What's the steepest it ever gets? If you had to draw tangent lines in here, what would be the slope of that tangent line? I don't know, like -4, -5, something like that. Sure, -4, -5 is somewhere in here. Maybe the steepest it ever gets is something like that, and then it comes back up to this point. Again, I'm not too worried about the shape of the line that you draw in blue. I just want to make sure that the height of the line you draw in blue is always a negative number to illustrate that the original graph is decreasing on this interval. What about my next interval from this critical value to this critical value? Well, the hiker's going uphill, the graph is increasing, so my first derivative is positive again. If you think about how positive it gets, maybe you'd end up drawing something that looks something like this, very loosely speaking. I can do that same analysis on the next few intervals. From this interval to this interval, my graph is decreasing, although it's never decreasing all that much, so maybe it just goes a little bit below the axis and looks something like this. On my next interval, I'm increasing ever so slightly, so the graph in blue is above the axis ever so slightly. On my next interval, it looks like I'm decreasing. What's the most it's ever decreasing? I don't know, somewhere in here it seems to be decreasing as fast as it's ever decreasing. What's the slope here? I don't know, like -2 or 3 or so. Maybe I draw it to look something like this. I'm getting pretty close to the end here. The interval in between these two critical values, it's increasing the entire time. And somewhere in the middle here, it's increasing as fast as it's ever going to be increasing. And it's increasing pretty damn fast. So the height of the line in blue should be pretty big. I don't know, something like that maybe. And then I have this last interval on which it's decreasing. Maybe I'd sketch my graph to look something like this. Is what's pictured in blue a perfect depiction of the first derivative? No, absolutely not. But the height of the graph in blue is positive where the first derivative is positive, and the height of the graph in blue is negative where the first derivative is negative. And I've even incorporated some ideas of the magnitude of how positive and how negative it gets. I think this is a pretty good depiction of the first derivative. Don't believe me? What I did is I took Desmos and I calculated the function and its first derivative and sketched those side by side. And I think what you see in blue here is pretty similar to what you see in blue here. I mean, the magnitudes are a little bit off, but everywhere the graph in blue is positive up here, it's positive down here, and everywhere it's negative here, it's negative down here. If you can do something kind of like that, I think you've picked up the hardest concept in this section. Before I end this video, I want to do one more thing. We took the function and we sketched the derivative. Wouldn't it be cool if we could take the function and sketch the second derivative? Well, it turns out that you can. We could sketch the second derivative just like we sketched the derivative without knowing the equation at all and just looking at the function. It's just a little bit hard to do. If you think about how we started out coming up with this graph in blue, we first figured out all the zeros of the graph in blue. Zeros of the graph in blue corresponding with critical values of the graph in red, because the graph in blue is the first derivative. But we don't want to sketch the first derivative, we want to sketch the second derivative. So if we want to know when the second derivative equals 0, we're not looking for critical values of the graph in red, we're looking for inflection points of the graph in red. Unfortunately, inflection points are a little bit harder to see, but I think we'll be able to do it. If you look at this graph in red here, right, it's definitely concave down in this region, and it's definitely concave up in this region, but there's some point, and it's really hard to identify exactly where that point is, but maybe, I don't know, somewhere in here where my graph switches from concave down to concave up. And then there's another point, roughly speaking, in here where my graph switches from concave up to concave down. I'm an upside down bowl until I get to a point somewhere in here, at which point I switch to a right side up bowl until I'm somewhere over here. Now I'm back again as an upside down bowl until I get somewhere in here, back to the right side up bowl until, I don't know, here-ish, give or take. And then finally I'm an upside down bowl the rest of the way. These points pictured in green are inflection points on the graph in red, and therefore there's zeros on the graph in green. I'll make them a little bit bigger to try to make this obvious. When I sketch my graph in green, I got to make sure I go through all these big green dots. But like we saw above, it wasn't enough to just figure out these blue dots. We had to figure out when we're between the different blue dots, should we be above or below the axis? We have to do the same thing down here. We have to figure out, should I be above the axis or below the axis as I'm connecting all the big green dots. Up here, the way we figured out if we should be above or below the axis is by looking at the graph in red and figuring out whether it's increasing or decreasing. Down here, what we're going to do is look at the graph in red and not consider whether it's increasing or decreasing, but instead consider whether it's concave up or concave down. My graph over here is concave down. Some shorthand notation for that is CC down. Between this point and this point, my graph in red is clearly concave up. From this inflection point to this inflection point, I'm concave down again. And I continue to alternate as I go across my graph until I get to this last region here where the graph looks like an upside down cereal bowl, if you want, and therefore is concave down. Measuring how concave the graph is really hard. So it's really hard to figure out the magnitude of the values that I want to plot in between these different inflection points. I know, for example, that I'm concave up on this region, so I should definitely have positive values in here, but should it look like this, or should it look like this, or should it look like this? Frankly, it's really hard to figure it out by just trying to analyze the second derivative. But there's a little trick you can do. Instead of thinking about the graph in green as the second derivative, a way we can think about the graph in green is it's the derivative of the derivative, right? That's what the second derivative means. Instead of thinking about it's the second derivative of the graph in red, think about the graph in green is the first derivative of the graph in blue. We didn't need to do any of this analysis that we did on the graph in red down here. We didn't need to locate inflection points and figure out if the graph in red is concave up or concave down. What we could have instead done is completely ignore the graph in red and just look at the graph in blue, the first derivative. Instead of looking for inflection points on the graph in red, look for critical values on the graph in blue. Points where the graph in blue are at a mountaintop or at the bottom of a valley. Points where the tangent line to the graph in blue would be horizontal. And what you'll see are all those points, the critical values of the graph in blue, the critical values of the first derivative, correspond with inflection points of the graph in red. If you can see why that makes sense, because the second derivative is the derivative of the derivative, you're understanding concepts which frankly tend to blow students' minds. Pretty wild. If we completely ignore the graph in red, just focus on the graph in blue, then when we're looking at this region, we're not saying it's concave down on this region because we're not looking at red. We say it's decreasing on this region because we're looking at the graph in blue. How much is it decreasing? Well, it's decreasing pretty quickly over here, but it's hardly decreasing at all over here or over here. The graph in blue is decreasing on this interval, so the height of the graph in green will be a negative number. It's decreasing really quickly in here, so it'll be a large negative number in here, whereas it's decreasing really slowly here and here, so it'll be a small negative number. At those points, my graph in green, very loosely speaking, will look something like this. As I move on to my next interval, trying my best to ignore red and just look at blue, I'll think about my graph in blue as increasing on this interval. I'll try to get an idea of the magnitude at which it's increasing, and I'll draw something more or less like what you see here. In my next interval, I'm not thinking about the graph in red as concave down, but instead thinking about the graph in blue as decreasing. It's decreasing all the way until I get to this point. Then I'm increasing. Then I'm decreasing. Then I'm increasing again. And then finally I'm decreasing for the rest of the graph that's pictured. We can get a rough idea of the second derivative by looking at the function itself, but it's really hard to do because it's hard to see concavity. So a better way to get a rough idea of what the graph of the second derivative looks like is by analyzing the first derivative in the same way that we analyze the function to come up with the graph of the derivative itself. Yeah, this stuff gets kind of intense.